I believe it's true to say that in operating the power plant, the operators do not pay too much attention to the generator. Whether the generator is driven by a steam turbine, gas turbine, or even a water turbine, it is an extremely reliable piece of equipment which continues to produce electricity while demanding very little attention from the operator. It seems that most of our activities are focused upon the turbine end, while the generator looks after itself. But we should never allow ourselves to forget that certain operating features of the generator are extremely important. And for this reason, it is necessary to brush up on this subject from time to time. In this videotape, we're going to take a look at typical construction features of the power generator and also discuss important factors related to operation and control. The purpose of the generator is to receive the rotating mechanical energy which is produced in the turbine and convert this into usable electricity at a specified terminal voltage. All modern power generators produce three-phase power. We'll be discussing this in greater detail later in this tape, but at this point, we're focusing our attention on the physical arrangement of the components which make up the generator. The electricity is actually produced in the stator winding. This is the stationary winding which is supported by the stator frame. The stator winding consists of insulated copper conductors which are embedded in the slots of the stator core. The slots run end to end. The so-called iron core is made up of laminations of special steel. Each individual lamination or plate is coated on one side with an insulating material. The objective of this is to reduce the flow of induced eddy currents through the core. This in turn reduces the heat loss of the iron core and thus keeps the temperature down. The laminations are tightly packed together and secured within the stator frame. Once the stator bars are fitted into the core slots, they are joined at the ends to form continuous coils or windings. These end connections are referred to as end turns. The conductors are securely held in the slots by wedges of insulating material. This is extremely important, as the windings themselves are subject to quite heavy mechanical forces during operation. The windings may try to twist during heavy power surges or electrical faults on the power system. Similar distortion of the windings may occur if the generator is badly synchronized, that is, synchronized when out of phase with the system. One of the few problems that can occur on generators is the loosening of the windings, with resultant vibration and increased temperature rise and perhaps damage to insulation. The stator conductors are connected together in various series and parallel arrangements so as to produce the rated terminal voltage, say 13.8 kilovolts, and rated current output, say 6,000 amps. The stator windings are connected to the terminals usually at the bottom of the generator. Outgoing conductors will be connected at these terminals in order to carry power to a bus or power transformer and perhaps an auxiliary transformer. VTs, voltage transformers, are also located close to the terminals to provide input to the generator voltage control system. Current transformers are usually located close to the terminal bushings. These CTs measure the value of current and transfer this information to the control and protection system. In some generators, surge capacitors and lightning arresters are located at the terminals so as to protect the generator windings. Heat is produced within the generator in three ways. Current flowing in the stator winding produces heat called I²R copper loss. Friction between the spinning rotor and the air, or hydrogen, in the generator produces heat called windage loss. Stray induced current in the iron core produces heat called iron loss. If the internal temperature rise is too high, it will damage the insulation and put the generator out of service. For this reason, distinct limits are placed on permissible temperature rise. In order to monitor this, temperature detectors are embedded in the stator windings at the anticipated hotspots, and these readings are continuously recorded and alarmed when necessary. Forced cooling is employed to keep the temperature rise as low as possible, either by hydrogen cooling or air cooling. We'll be talking more about this in the next segment, but first, let's move our attention to constructional features of the rotor. The function of the rotor is to provide a rotating magnetic field. The rotor is coupled to the turbine and thereby receives all of the mechanical energy. This mechanical energy is then transferred across the rotating magnetic field to the stator windings, where it is converted into electrical energy. The rotor is supported at each end by journal bearings. These must be very accurately aligned so as to maintain the same precise clearance between rotor and stator all the way along the length of the core. A forced lubrication system is required for the bearings. Pressurized lube oil may be provided from the turbine lube oil system, or in some cases a separate generator lube oil pumping system is installed. On many units, the top of each journal bearing is vented through a vapor extractor. This creates a slight vacuum inside the bearing and so prevents any oil vapor from accumulating inside the generator housing. So the rotor provides the rotation, but where does the magnetic field come from? Well, I suppose this could be provided by a permanent magnet, but this would provide no means of control, and probably the field would not be strong enough. In actual fact, the magnetic field is created by a rotor winding. Insulated solid copper conductors are embedded in rotor slots, and they are located in such a manner as to form a huge coil which turns with the rotor. DC current is passed through the rotor winding in order to produce a magnetic field with a north and south pole. Of course, the next question is, where does the DC come from? Well, there are two possible sources depending upon the design of the machine. A common arrangement is to provide DC from a rectifier located in a nearby panel. This is known as static excitation. The DC is applied to the rotor winding through brushes running on collector rings. An alternative source of DC excitation is from a shaft-mounted exciter. In this case, connection leads are run inside the shaft, and therefore no brushes or collector rings are required. The magnitude of DC current and voltage applied to the rotor windings is quite low, say 600 amps at 250 volts. Typically, the generator will be housed in a compartment like this. Access is provided to allow maintenance and inspection of the collector rings or brushless exciter. This particular generator is air-cooled, and the air is in turn cooled using water carried in these pipes. Generally, in modern installations, the generator rotor is directly coupled to the turbine shaft. However, some turbines are designed to run at much higher speed, say 5,000 to 7,000 RPM. In this case, the generator is coupled through a gear drive in order to drive the generator rotor at the correct speed, that is 3,600 RPM for a 60 hertz generator. But what is it that determines the speed requirement? Well, we'll talk about this later. For now, let's take a break. Please switch off the tape and review this material in your workbook.